Good afternoon, ladies and gentlemen. My name is Ram Venkatadri. I am the Global Marketing Manager from Paul Corporation. I've been with Paul for about 8 years now, and I have 25 years experience in the chemical and petrochemical industry. I'm based in Paul's New York office. Today we will be discussing liquid-liquid coalescence and filtration that goes with the coalescence in the chemical and petrochemical industry. I will show you several examples from these two industries where we use liquid-liquid coalescers. I hope you will enjoy it. So as you can see, the webcast today will focus on filtration and liquid-liquid coalescing fundamentals. After that, we will talk about some specific products that Paul offers for filtration as well as for coalescence. Once we have covered that, we will go into specific applications. In the petrochemical industry, we have a very common application in ethylene plants known as quench water treatment or process water treatment. After that, we will cover water removal in 3 different applications in the petrochemical industry. Water removal in aromatic plants and from feed naphtha as well as from liquid propane. After that, we will discuss some chemical applications. A common one would be the oil removal from liquid ammonia. There's also an example from the hydrogen peroxide industry, water and organics removal from hydrogen peroxide. So these are the topics that we will cover today. So we come to the section now on particulate filtration and the basics of coalescers. This is the most fundamental equation governing the principles of filtration. It's known as Darcy's law. Here we show that the pressure drop of any filter is directly proportional to the flow rate of the liquid going through it. It is directly proportional to the viscosity of that fluid and also to the depth of the filter that it's passing through, the thickness of the filter. It's also inversely proportional to the surface area of the filter. So if you had a very high surface area, you're going to get a very low pressure drop. So it's an important principle to remember. Here's an example of what is known as a depth filter. It has continuously graded pores with the outer pores being the largest in size, and then the pores are becoming smaller and smaller in size as they trap smaller and smaller particles. So the flow is from outside to in. The combination of this continuously graded pore and a high performance inner section gives you a very low pressure drop. It also comes in a coreless design where we have a permanent steel core in the middle, and the elements are simply pulled up over the core after it has reached a terminal pressure drop, and then they are replaced. Now we discuss pleated filters where you maximize filtration area to get the lowest pressure drop. On the left-hand side, what we call as a fan pleat filter is being shown there. It has a high surface area, something like 54 square feet. The flow is outside to in. The typical filter media is epoxy cellulose. It can withstand a temperature of 275 degrees Fahrenheit, and it's good for hot water filtration. It can also be made from glass fiber as the filtration media. On the right-hand side, you see a specially designed crescent-shaped pleated filter. It's known as UltiPleat. It leverages Paul's patented pleat design to maximize surface area. One such filter can replace as many as 30 depth filters. The flow pattern here is from inside of the filter to the outside. And so the contaminants that are captured are contained within the filter. Now we will discuss liquid-liquid separation. Oil and water are immiscible. On the left-hand side, oil is the continuous phase, and water droplets form a tight emulsion of water and oil. There is a third component in here. It's called a surfactant, which are naturally occurring surface active agents. They could be present in the oil, or they could be introduced, for example, as chemical additives. These surfactants absorb on the water molecule and they stabilize the emulsion, which means it's hard to break the emulsion. On the right-hand side, it's the opposite case where you have an oil in water emulsion. So now we have to break these emulsions in order to separate the oil and the water. Let's look at the principles of coalescence here. The flow is from the left side to the right side. The solid particles that you want to remove are shown as yellow rectangles, and they are captured within the layers of coalescence. The oil or water droplet that you want to remove is a very fine blue dot there. It goes through various stages of coalescence and enlarges in size in each of those three layers that you see there. So it can go from the left-hand side as a very fine 0.1 micron droplet all the way on the right-hand side. After the secondary coalescence stage, it is 1 millimeter in diameter, and then it's detached. So you can see that the principle of separation is totally mechanical in nature. This slide reinforces what was mentioned on the last one. How does a liquid-liquid coalescer behave? The first thing it does, it captures the small droplets. The initial capture of the fine droplet is an important measure of the efficiency of a coalescer. This is where the coalescer is much better than your conventional separation devices like a knockout drum or a vane pack or a mesh pad. The second stage would be the growth of the droplets into a large drop size of 1 millimeter. The third stage would be the release of these droplets, and the fourth stage is the separation either by a gravity method or by a barrier method known as a separator, which we will describe. This is a very busy slide that describes the principles of separation. Interfacial tension is an important parameter that defines how stable is the emulsion. If your interfacial tension is less than 5 dynes per centimeter, emulsion is very stable and hard to break, and the droplet sizes are quite small. The surfactants that are present can cause this problem. There is a traditional glass fiber coalescer that is susceptible to something called disarming. The coalescer, as you know, has active sites where droplets are supposed to be captured. Instead, the surfactants neutralize these active sites, so the droplets are not captured. And the glass fiber coalescer is known as being disarmed. So what happens is it does not break the emulsion anymore. In the chemical industry, interfacial tensions are often quite low, and so it is a big challenge for the traditional glass fiber coalescer. One way to overcome the problem of the disarmed coalescer is to use polymeric material. Paul's coalescers are all polymeric in nature. They can handle very low interfacial tensions of even 1 dyne per centimeter. Most of the time, these coalescers will last at least 1 year in service, and they have to be replaced when the terminal pressure drop is reached. Now, it's important to remember that these coalescers remove free water or free hydrocarbons. They don't remove the dissolved water or the dissolved hydrocarbons. In the case of water removal, we can guarantee that these polymeric coalescers will reduce the free water to below 15 parts per million. And free water can be measured by what we know as the aqua glow method. The total water content can be measured by something called the Carl-Fisher titration. In the case of oil removal, these Paul coalescers can remove consistently the free oil below 20 parts per million. And an established test for the oil and grease would be the EPA 1664A using N-hexane as a solvent. So this is a typical picture for a liquid-liquid coalescer. There is a pre-filtration stage ahead of the coalescent stage, and the coalescer in this case happens to be horizontal in design. A pre-filter is an absolute must for any coalescer. You want to remove any solid particulate matter, otherwise it will go into the coalescer and the coalescer will behave as a filter and filter the solids out. The job of the coalescer is to break the emulsion. Therefore, it is necessary to have a pre-filter ahead of the coalescer in every case. And we have different designs for the pre-filter. We discussed in an earlier slide about depth filters as well as pleated filters. The pre-filters can be vertically mounted or horizontally mounted. Normally, it is vertical. As far as the coalescers are concerned, there are different types of coalescers which we will discuss in the next few slides, but they are there to remove the free water or the free hydrocarbon, and they come in horizontal or vertical configurations. So here you see an example of a horizontally mounted liquid-liquid coalescer with a pre-filtration step ahead of it. In the coalescer, you see the housing there. The housing size is determined by several parameters such as interfacial tension of the fluids, the viscosity, and the specific gravity of the liquids. You see a coalescer followed by a large settling zone for the droplets to be disengaged. So within the coalescer, the flow is from inside to the outside. The droplets become larger and larger as they go to the outside, and then they disengage, as we discussed earlier, and then they drop down in the gravity settling zone. This kind of horizontal configuration is typically used for removing oil from water, or if you want to separate two non-aqueous liquids, such as oil and ammonia. It's also used when the interfacial tension is very low, less than 5 dynes per centimeter. Here is an example of a vertically mounted liquid-liquid coalescer with a pre-filtration stage ahead of it. In this case, you can see the coalescer on the right-hand side, and there is a device called a separator, which is located directly below the coalescer stage. This kind of configuration is used when your interfacial tensions are higher than 3 dynes per centimeter and typically used to remove water from oil. So the emulsion will flow through the coalescer. The water droplets will become larger and larger and they become disengaged from the coalescer. Then they go into the separator device, which happens to be hydrophobic. It will also reject the water. And the oil will flow through the separation device. Both the water and the oil are removed by separate drain connections. So what you're seeing here is the separator, which is used in lieu of the settling zone that you saw in the horizontal design. Here you see the Sept coalescer. It is a versatile product that is used in the chemical and petrochemical industry quite a bit. One of the challenges in these markets is that the liquid that you're trying to filter or coalesce has to be compatible with the media of the coalescer. In this case, it happens to be fluorocarbon media, and even the end caps can be made of fluorocarbon or with stainless steel. This phase Sept coalescer can withstand temperatures up to 300 degrees Fahrenheit, which is quite a bit, and it can also withstand a wide range of pH and chemical compatibilities. Its dimensions are 3 3/4 inch ID and 40 inches long. Here's an example of the phase Sept Y coalescer. It's a special product that's used in several chemical markets, such as in ammonia, urea, and nitric acid. This coalescer media is made of polyolefins, and the gasket material is made of EPDM, which can withstand an ammonia environment. It has a temperature limitation of 122 Fahrenheit, which is much lower than that of phase Sept that you saw on the last slide. Its dimensions are 2 3/4 inch ID, 20 inches length, and its common applications is in the chemical industry. Here's another versatile coalescer known as the Sept family of coalescers. Here, the material for the coalescence is made of polyester, and this product has a temperature limitation of about 140 Fahrenheit. Has a dimensions of 3 3/4 inch ID and 40 inches length, very similar to the phase Sept product that you saw 2 slides earlier. The Sept family of products can be used to break emulsions with interfacial tensions as low as 1 dyne per centimeter. There is a special coalescer called the Sept XS within this family. It can take very high flux rates, so you need less number of elements to do the same job, and it's our newest coalescer. Now let's start looking at some specific applications. We'll start with the petrochemical applications first. Processing of quench water in an ethylene plant is a classical application for filtration and coalescence. The quench water or the processed water contains solid contaminants such as coke and tar. It also has an emulsion of oil and water, the oil being called pyrolysis gasoline. The interfacial tensions are quite low, well below 5 dynes per centimeter, so it's very challenging. So first we have to remove the coke and the tar, and then we have to break the emulsion of gasoline in water. If we don't do that, then the downstream units will be negatively impacted. These downstream units consist of heat exchangers and reboilers. They will be filled with polymer from the oil, and then it also requires a use of excessive amount of steam in the steam stripper to do its job, as well as it produces a lot of wastewater that requires treatment. All of these problems will be resolved if we can break the emulsion of oil and water and remove the solids. Flow chart for the ethylene quench water. You see the furnace on the left hand side, and there are 2 quench towers, oil quench and water quench towers following the furnace, and then there's a decanter, which is really a vessel which has oil, water, and solids. From the decanter, most of the water coming off the bottom of the decanter is recycled back into the water quench tower. But a small portion of that water is used for making steam, and that's called quench water. What you see on this drawing is it is being treated with 2 sets of pre-filters followed by the liquid-liquid coalescer. So the pre-filters will remove the coke and the tar, and the coalescer will break the emulsion of gasoline and water. So all the problems downstream will be solved by doing this. We have 40 successful installations around the world doing exactly this application. It's a very common one in ethylene plants. Here we are seeing some typical results from field testing of these quench waters in ethylene plants. The samples were collected at various points, at the inlet of the coalescer, at the outlet of the coalescer, and also the different fluids that were collected from the coalescer. the separated fluids. Now the bottle on the right hand side contains the feed. You can see it looks like milk. It is an emulsion of oil and water with very low interfacial tension, and it has some solids, fine solids. The bottle in the middle is the separated oil or the gasoline that we were able to collect from our coalescer. You can see it looks chocolate brown, and that is the color of the pyrolysis gasoline. The bottle to the left is the clean water that comes out of the coalescer, containing less than 20 ppm of oil and water in the emulsion and almost no solids. You can see what a difference the coalescer makes, and this is why they use it commercially. Here's another application downstream of the ethylene plants. So you see the settling tank there. This is what we discussed on the previous slide. This is the oil water separator, which gets the water from the quench tower. From the bottom of the settling tank, you get the water with the pi gas. The pi gas is the component to be removed. That's what we just talked about. But if you look at the stream from the top of the settling tank, this is the pyrolysis gasoline or pi gas with some water contamination in it. The water contamination could be just a few ppm to as much as 2 or 3 weight % of water. Now this gasoline is going straight into the aromatics plant to make BTX, benzene toluene xylene. And the problem is that this water would interfere with some of the catalysts that are involved downstream. So once this water and oil emulsion goes downstream, it goes into a noble metal catalyst, usually palladium, which is used for the hydrogenation reaction of the pyrolysis gasoline to make BTX. Now, the presence of water deactivates this catalyst, and it has to be reactivated quite frequently, which damages the efficiency of the catalyst. The other issue is that the emulsion itself, the water and oil emulsion, is very, very low in interfacial tension, somewhere in the 5 to 10 dynes per centimeter. Another complication is that there could be caustic in this stream, caustic coming from upstream processes, which makes it difficult to break the emulsion. As I said earlier, the water content could be anywhere from low ppm, which is like 100 ppm, all the way up to 3 weight %, which is 30,000 ppm. So this is the water we are trying to remove here. And the solution here is to use a pre-filter to remove the solids, and then followed by a phase Sept coalescer, which can withstand all of these conditions. And you can see the picture there on the right of this process. So this installation is there at about 15 plants currently around the world. This is another application. This is naphtha feed treatment. This is the naphtha feed going as feed to the furnaces in the ethylene plant. This naphtha usually is imported into the plant via barges or ships and contains corrosion products that it picked up along the way, iron compounds. Also has a lot of water in it. Normally this naphtha is sent into a settling tank to remove the water, but the settling tank does not do a very good job. Also, there is salt in the water, and the sodium in the salt is a major issue in the furnace because it accelerates coke formation in the furnace. So the impact of all of these contaminants on the ethylene furnace is major. It can cause rapid decoking and therefore destroys the efficiency of the furnace. Also, it can form incomplete combustion products such as carbon monoxide and off-spec ethylene. Finally, it may result in so much corrosion that you may have to replace the furnace tubes in the radiation section. So a range of issues here. So a solution for the naphtha feed problem is shown here. This is from an ethylene plant in Western Europe. You can see the Paul pre-filter there standing up vertically, and that's the pre-filter to remove the corrosion products in the naphtha. And then there is also the vertical liquid-liquid coalescer, the Sept coalescer that is being used here. That's the one that separates the water from the naphtha before the naphtha is sent into the furnace. It works very efficiently on a very large flow rate of naphtha. We have several installations of this nature. Here's a case study that describes naphtha feed filtration. This was in a Dow Chemicals plant in the USA. The flow rate, as you can see, is very large. The naphtha feed was 2,900 gallons per minute, and the filter and coalescer increased the decoking cycle from 40 to 55 days. So the furnace became a lot more efficient since it ran for a longer time. Dow estimated that it saved them $2 million per year, and whatever the installation cost, it was paid back in less than 10 months. And there were many benefits as a result of that. You can see some of those benefits outlined there: the reduced fouling and the lengthened furnace tube life and lower carbon monoxide formation. We'd be happy to send you a copy of this paper if you're interested. Now we will switch gears a little bit and look at a relatively new process called propane dehydrogenation, better known as PDH. This field is dominated by two licensors, UOP with their Oleflex process and CB&I Lummus with their Catafin process. In both cases, propane is dehydrogenated to form propylene and hydrogen. So this is a new way to manufacture propylene in lieu of steam cracking. In this process, you can see the block diagram down there. You have liquid propane going into a molecular sieve bed, which removes all of the water in the propane. And then it goes into a dehydrogenation reactor with a catalyst in it, and the reaction takes place to produce propylene in that reactor. Where Paul comes into the picture is the fact that the molecular sieve bed can be subjected to excess of water loading, and we are trying to eliminate that by removing the free water before the propane goes into the molecular sieve bed. The free water can be reduced to almost zero with our liquid-liquid coalescer, so that the molecular sieve bed can perform much better and take out the dissolved water. So Sept XS or phase Sept coalescers can be used for this purpose, and this is being practiced commercially now. Now we will switch our attention to a couple of chemical applications. So far we have looked at 4 petrochemical applications. Now we will focus on 2 chemical applications. Let's look at the case of removing oil from liquid ammonia, which is a common application for liquid-liquid coalescers. Ammonia, as many of you may know, is made by the conventional Haber process, where you react nitrogen and hydrogen in the gas phase over the catalyst to form ammonia. These gases pick up compressor lube oil, and this oil stays with the ammonia product. The ammonia is liquefied after a refrigeration step, and then it is stored. It contains this unwanted oil. This slide shows you some of the reasons why we need to remove the oil from the ammonia before it is processed further. Nowadays, the specifications call for 5 to 10 ppm of free oil in the liquid ammonia. In fact, 5 to 10 ppm of total oil in some cases. In urea plants, this oil goes and clogs up the strippers and high-pressure injector nozzles with the polymeric deposits from the oil. So we have to remove this oil. In nitric acid and caprolactam plants, they flash this liquid ammonia before they make the product, and during that process in the vaporizer column you may see deposits formed from this oil. So these are some of the reasons for removing the oil. Here we show how we actually remove the oil from the ammonia. The liquid ammonia is stored in tanks which are either cylindrical or spherical. Here we show a cylinder. There's a small layer of oil at the bottom of the tank, and liquid ammonia is on top of it since it's less dense than the oil. If you do nothing, then this liquid ammonia is sent to downstream plants or it is sold. But if you wanted to process it, it is sent through a pre-filter which can remove the solids, whatever solids there are, and then through a liquid-liquid coalescer which is compatible with the ammonia, and it reduces the free oil to almost zero. So whatever you get out of the coalescer is just the dissolved oil. You can sell that stream or you can send it back into the tank. Phase Sept Y is the coalescer that is commonly used in this application. Now we move on to the hydrogen peroxide industry. Those who are from that industry will recognize this simple flow chart. There are two applications here for liquid-liquid coalescers. The first one is the removal of water from organic working solution, and the second is the removal of organics from crude hydrogen peroxide. Now if you look at the drawing that we have there, there is a hydrogenator reactor on the left-hand side, where you react the working solution, an organic solution, with hydrogen. The catalyst that you get downstream is captured in various Paul filters, and then it goes through an oxidation step and a liquid-liquid extraction step. The working solution is recycled back into the reactor, a hydrogenation reactor, and our objective here is to remove the water from the working solution. That's what you see circled as number 4. So here we are trying to remove the free water, which could be as high as 5,000 ppm in the working solution. In the second application, further downstream, we are trying to remove the working solution from the crude hydrogen peroxide product. In either case, we use Phase Sept coalescer, and it works pretty well. So this is the final slide. So far you've seen several examples of applications in the chemical and petrochemical industries. Due to lack of time, we did not have an opportunity to go further into this topic, but I'm sure you'll have some questions. For your information, I have provided my contact information below. So I wanted to remind you that this is an on-demand presentation, and it will be stored in the website for one full calendar year. You can go in there and access it and listen to it anytime. Now it's question and answer time. I've received a number of questions from you during the presentation. I may not get to all of them, but I'll try to read out the questions and provide answers in the few minutes that we have available. So thank you very much, folks, for attending the webinar. We do have some questions here, and I'm going to read out the questions that I wrote down during the presentation, and I'll try to provide an answer. We don't have that much time, so I won't be able to get to all the questions, but we'll do the best we can. The first question was, is there a reliable method to calculate interfacial tension? We have had good success with a method called the Dunoy ring tensiometer. It's the standard way of measuring interfacial tension. So what you do is you place tensiometer in the interface between the oil and water, and there is a ring that you place there, and the tensiometer applies a progressive force to pull the ring off the interface. That force is then calibrated to in units of interfacial tension. So the lower the number, the harder it is to break the emulsion. The next question I had was, what are the points to be considered in the scale-up of the liquid-liquid coalescer? That's a very good question. Paul has developed many sizing programs to evaluate this one, but for that you need a number of parameters to be input into the program: viscosity, density, interfacial tension, and flux, which is the flow per element, are among the most important parameters to consider when you're scaling up the liquid-liquid coalescer. It is important to size a coalescer effectively, otherwise liquid removal efficiency will be affected, sometimes drastically. Now, historical data with established parameters on applications that are repeatable are frequently used for sizing. For example, we talked about the oil in ammonia. We have a lot of historical data there that we can use for the sizing. Now, we also have several test rigs that can be brought on site to customer locations. And these test rigs can be used to develop some field data that can then be scaled up easily to simulate what goes on in the real world. We also have rental fleets that are now available, so we can actually go on a full scale and use these rental fleets for a little while until a permanent installation can be established there. So there's a number of things that we can do here, but sizing is a very important parameter. The next question I had was, is there an upper limit of free water that a liquid-liquid coalescer can effectively remove? By the same token, is there an upper limit on free hydrocarbon that a liquid-liquid coalescer can effectively remove? Well, once again, a very good question. As noted, discontinuous phase loading of up to 3 weight% is assumed for most of the sizings. So you can go up to 30,000 ppm of the phase that you want to remove, whether it's the oil or it's the water. Beyond that, it is not recommended. But 30,000 ppm, you'll agree, is a lot. Now, this separation has worked very effectively, and sometimes you need to oversize the housing a little bit to handle even larger volume of the phase that you want to remove, which is the discontinuous phase. But however, we usually recommend to customers to stick to the 3 weight% limit. The next question I had was, what is the ppm level of hazing of the product? So when do you see visually when the coalescer is done well? There is something called clear and bright standards. So if you have freedom from visible solids and water droplets and a sparkling cleanliness, then your coalescer has done the job. Now, if you have a trained eye, you can see that the haze can be coming on even as low as 20 ppm of free water. Normally, the untrained eye will notice these haze levels at 30 to 40 ppm. But the standard in the industry is clear and bright water. There are other questions as well. For example, I'm reading it here. How does a Paul coalescer, such as an Aquacept XS, compare with a membrane separator with a 0.5 micron hydrophobic membrane? Thank you for the question. I think you know our products fairly well to ask this question. A high-efficiency liquid-liquid coalescer is excellent for analyzer protection. The protection is from solids or from removing of free water or free oil. But a zero point 0.5 micron very fine membrane filter can provide much better protection even for the dissolved contaminants. So that's the difference. The membrane takes out everything, whereas the coalescer will remove only the free water or the free oil. So that's the limitation that you have with the coalescer. I have one more question here. Do vertical coalescers require level control on the aqueous phase being removed, similar to a boot on a horizontal coalescer? Oh, that's an excellent question. Now, a vertical coalescer will have, as you saw in the picture, you'll have the coalescer at the top and you'll have a separator element at the bottom. So the liquid that is separated out has or accumulates at the bottom of the element, between the bottom of the element and the lower tube sheet. So it is similar to a boot on a horizontal coalescer. Now, for both the vertical design and the horizontal design, it is important to have the ability to drain the accumulated phase that you're removing. So you can drain it manually, or you can drain it in an automatic way, depending on how much volume there is that is collected. On most applications, automation may be required if there's a lot of liquid that is being collected. I have one more question here. Gentleman wants to know the present technologies remove free and dispersed hydrocarbon, but does not remove the dissolved highly saturated hydrocarbons. Should this be removed? Yes, the highly unsaturated hydrocarbons, the dispersed phase can be removed in a downstream unit such as a steam stripper. The free hydrocarbons can only be removed by our coalescer. So we need to have a device to remove the dispersed phase or the dissolved phase. So that I hope I provided the right answer to that question. Okay, I'm still have a couple of minutes more. If you have any questions, you can write it in and send it. Okay. If there is no more questions, I would say we have come to the end of this webinar. I want to remind you that this presentation will be stored as an on-demand presentation, and you can log in the same way that you just did to access it, and it will be there for one full calendar year. This is a recorded presentation, so you should be able to access it anytime. Thank you very much. Bye now.